Here we're going to look at specific heat capacity, and in this series of experiments we're going to look at the amount of heat energy that's required to change the temperature of an object. And so what we have is we have a joule meter. So joule meter will measure the amount of energy. It's going to measure in kilojoules. There's a heater which is connected to this, the beaker which is lagged. Now lagging is something that you'll hear, is a term you hear used a lot. It just basically means that it's insulated to prevent heat loss. Inside the beaker we have a temperature probe in the water which is connected to a digital thermometer. When I switch it on, I'll switch it on now, you can see that as the heater heats up it's going to measure the energy, measure the temperature rise, and it'll plot a graph as we go. Now we've come back to this a little bit later, and what we can see is that it's quite clear that the relationship between the heat energy supplied and the rise in temperature of the water is a directly proportional relationship. So we'll have EH here, which refers to the heat energy. So energy, we subscript H, telling us heat energy. Backward swimming fish, directly proportional. And then this term here, you won't be familiar with this. This is delta T. So the triangle just means change in. And we would say that that is delta T. So change in temperature. The big T obviously being temperature. Now moving on to this one, we're going to look at how the mass of water, or the mass of any material indeed, will affect the amount of energy required to raise the temperature by a set amount. Now in this experiment it's saying how much heat is needed to produce a 5-degree temperature rise in different masses of water. What we're going to do, we're going to switch on each of the heaters. It's going to run exactly the same, and we're just going to see how much heat energy it will take to bring all of these up to, well, if they start at 18 degrees, how much heat energy is going to be required to bring our 0.2, 0.4 and 0.6 kilograms of water up to 5-degree temperature rise, so it would be up to 23 degrees. So we'll start them all off. And then we wait a while and just see how much energy is going to be required. Okay, the obvious benefit for you is that you didn't have to sit and watch as that slowly rose up. But what we can see here is that they're all at 23 degrees, and as you double the mass of water being heated, so as the change in temperature is the same, so delta T is the same, 5 degrees difference, and now as you double the mass of the water, you'll double the amount of energy. And as you triple the amount of water for the same temperature rise, you'll triple the amount of energy. And so by looking at this, we're going to say that heat energy is directly proportional to the mass of water that you're going to use again. Now finally we're going to look at the material and how a material will affect the amount of heat energy required. So what we're going to do, we have 3 different types of material. We've got copper on the left hand side, in the middle there's aluminium, and finally we have water. They're all connected up to the same power supply, and so they're going to be provided with the same amount of heat. We're going to switch them on and we're going to wait for a time of 3 minutes. Well, I'll wait for a time of 3 minutes and I'll pause this, and I'll come back 3 minutes later and we can look at what has happened. Okay, so I've got a stopwatch ready. I'm going to start that now, switch on the heaters, and I'll see you in 3 minutes. So we can see that after a time of 3 minutes, the temperature of copper has changed quite significantly, starting at 18 degrees, finishing at over 90 degrees centigrade. Aluminium still not as high as the copper, but higher, certainly a lot higher than the water. Okay, so what does this actually tell us? Well, if we go to, so we go to our paper. So what have we found so far? Well, I'm just gonna recap that the heat energy was directly proportional to the change in temperature. We also, sorry, that's not ET, it's EH. We have heat energy is directly proportional to the mass of the substance. And now we have this this thing that we have. There we go. That the type of material affects what we're doing. So, well, let's think about this for a second. We have a 50-watt heater, and we've raised the temperature for 3 minutes. So, the power of our heater is 50 watts, and we've done that for time 3 minutes. We can work out the energy that the heater is supplied in those 3 minutes by energy is power times time. So our power is 50 watts times 3 minutes, which we're going to convert into seconds, so 3 times 60, and that's going to equal 9,000 joules, or I'll say 9 kilojoules. So we've supplied 9 kilojoules to those substances. Now, if we go to, let's say, copper, they all start, can't see this, they all started at 18 degrees centigrade. And let's find out how far they all went. So we can see that the change in temperatures, the delta T for supplying 9 kilojoules to each of these materials over a period of 3 minutes, copper has the highest temperature rise and water has the lowest temperature rise. So we could actually work out exactly how much energy it would take. So how much energy it would take to raise the temperature of these materials by 1 degree centigrade. And this is a definition. This is the definition of specific heat capacity. So specific heat capacity, and we have this as C, is defined as the heat required so remember, heat is energy, so the heat required to raise 1 kilogram, raise the temperature so it's defined as the heat required to raise the temperature of 1 kilogram of a substance by 1 degree C. Okay, so each material will have its own specific heat capacity, and as a definition which you should go and learn, so the specific heat capacity is the amount of heat energy required that it takes to change the temperature of a material by 1 degree C, of 1 kilogram of that substance. Okay, so putting it all together, we have seen that the amount of heat energy required to change the temperature of something is determined by the amount of temperature change that you need. So if you need to make it hotter, it's going to require more energy. That's fairly obvious. Again, it's fairly obvious that if you have more of the material, it's going to take more energy to raise its temperature. Again, maybe not so obvious, but I guess it stands to reason that different materials will conduct heat in different ways. That you have something called specific heat capacity. And depending on the material will depend on how much energy it takes to affect that temperature change. So if we put it all together, then we can come up with a grand formula for the amount of heat energy. So we have EH is equal to C, which is specific heat capacity. I should have said that there. And that is symbol C, and C is measured in joules per kilogram. So remember, this little -1 just means per, so joules per kilogram per degree centigrade. Okay, so joules per kilogram per degree centigrade. And so we have EH is equal to C, specific heat capacity, M, which is the mass, delta T. So Cm delta T. And we'll look at a couple of worked examples, and we'll come back to this and we'll actually work out the specific heat capacities of these three materials in a later worked example. So here we'll look at a couple of worked examples, and our first one we'll do is how much heat energy is required to raise the temperature of 2 kilograms of iron by 10 degrees C. So we have specific heat capacity formula, which is EH is equal to Cm delta T. And what we need to do with all of these is we need to go and look up the C value. Now we'll get the C value from our data sheet, and we can see in the data sheet here that we'll have speed of light, speed of sound, gravitational field strengths, and then here we have specific heat capacity of materials. And so, and if we remember to our question, we were looking for iron, so we look up iron and we see that iron is 480 joules per kilogram per degree C. And so we can put that back in here. I'm just going to do a table so that we so 480, the mass we have 2 kilograms, and delta T is 10 degrees C. So it's just a question now of putting these numbers into the formula and then working out the answer. So C 480 times 2 times 10. And that will give us 9,600. And so I'm gonna be really careful, and something that I've noticed with the work that you've done so far, specifically when you were doing the conservation of energy work, that you should try and round a bit more. The energy answers are usually going to be a lot higher. You're going to certainly have in the kilojoule range or the megajoule range, and so you should try and round wherever possible. So this would be 9.6 times 10 to the 3 or we could just say 9.6 kilojoules. Second of our worked examples, we would have a kettle contains 1.5 litres of water. It's good to know that 1 litre of water is 1 kilogram, and so 1.5 litres of water would be 1.5 kilograms. It says if the initial temperature of the water is 20 degrees centigrade, calculate the heat energy required to boil the water. Now I hope you all are aware that boiling water is 100 degrees C. Okay, so what do we need to do? Well, we're going to start off with a table again. So EH is equal to, and we're going to be calculating the heat energy. We have C delta T. Again, we'll go to our table or our data sheet and find out the specific heat capacity of water. And we're going to look that it is water 4,180. So we have, if the power of the kettle is 2 kilowatts, how long would it take to boil the water? So here we're looking for a time, and in the brackets here, assuming no energy is lost. Now, this is relating directly to the learning outcome, which I'll show you just now. And that is, I can use the principle of conservation of energy to determine heat transfer. So, conservation of energy to determine heat transfer. Well, here in this case, we're going to have some electrical energy which we're going to take from the mains, from the kettle, and that's going to be transferred into the water. So we can use the principle of conservation of energy if we work out the amount of power drawn by using 2 kilowatts for a certain amount of time, and we can equate that to the amount of energy that's required to change the temperature of water in the kettle. And so we would have E, P, and T. This is a formula which we covered in the electricity unit. So our energy, now conservation of energy says that if it takes this amount of energy to raise the temperature of the water by 80 degrees, it's going to take that amount of energy from the power supply, assuming no energy is lost. And I'll come back to this a little bit later on. So we're going to have 502 kilojoules. Now we're not going to want to leave it as 502 kilojoules. I'm quite happy that we just do 502 times 10 to the power of 3 joules. Our power, 2 kilowatts, which will be 2 times 10 to the power of 3 watts. And of course, time is what we're looking for. So our formula E equals PT can be rearranged to T is equal to E over P. Make our substitution. 502 times 10 to the power of 3 divided by 2 times 10 to the power of 3. And working that out, will give us 251 seconds. Okay, so we can use the principle of conservation of energy to equate two sets of energies, assuming that no energy is lost. But what actually would happen if you tried this at home? Now, as you start boiling a kettle, well, the first thing that you're going to see is that you're going to see that the walls of the kettle will get hot, and so the heat energy is being transferred from first of all the heating element of the kettle into the water, and then the water is then going to be transferring some of its heat to the walls of the kettle. The walls of the kettle will then be transferring some of their heat out to the surroundings, and so if you go near a kettle, then you will be able to feel it's hot because it'll be heating up the air around it. And this is very much what you have to understand, that heat energy energy cannot be created nor destroyed. So energy is always conserved, but the heat energy is always going to try and equalize the heat of everything around it. This is, I mean, you'll know this principle from you have central heating in your house, that the radiators will become very warm, but then they'll transfer their heat to the air in your house, thereby heating up your house. And so what it will try and do is it will always try and equalize the temperature of its surroundings. Now, the kettle is insulated to try and minimize this heat. In this case, we would call it heat loss, because we're wanting to keep our time as short as possible. But in the terms of central heating, it's not heat loss, it's because it's going to heat up your house. And if you were to make a really, really simple example here. So if you were to have let's see, you had a block of ice. And so we've got our block of ice here at 0 degrees, and you had a cup of water at 20 degrees. Now, if you added the two together, what would happen is that the heat energy from the water, because the heat energy will always go from the hotter object into the colder object, so the heat energy from there is going to warm up the ice, and so we're going to have a scenario where we have our 20-degree water, our 0-degree ice, and the two are going to equalize, and so we're going to get to a situation where we have something like this. I mean, it could be, it might not be that, but you're going to have the water that cools down, so the water will lose energy, lose some heat energy, because it gives it to the ice to warm the ice up, and eventually you will have an equalization of the temperature of both substances. So back to our kettle, it says it takes 251 seconds to boil the kettle. In practice, because you're going to get, well, you definitely need 502 kilojoules of energy to raise the temperature from 20 degrees to 100 degrees. That's what you need. But we're assuming that this is what's supplied by the kettle. But because we're going to get some energy loss, i.e. some of the heat is going to escape into the surroundings, we're going to have to provide more than that energy, because we're going to lose some of it and we need to get that. And so in practice, we're going to need more of that energy. So this time here will be longer. Okay? And that is the principle of conservation of energy. So there will now be lots of problems for you to do in the course notes. There will, of course, be another video of me working through them. But thanks for watching, and I hope you've enjoyed this. Okay, bye.